Hi, my name is Daniel Findleton, student ID 100716573. Here again with Advanced Computer Graphics at Ontariotech University, and here I'll be showing off Challenge 4. So this challenge looks at computer vision through the OpenCV library, and so as you can see right now, I am displaying my current live feed. This is taken directly from the webcam and is picked up by the program as part of the template that Dr. Hogue gave to us. So let's just go over some sort of basic image effects and post-processing and utilities before we'll get into camera calibration. Unfortunately, I wasn't able to do the stereo calibration for reasons that I'll get into later. So I'll take the L on that portion of this challenge. But so let's get started. So first, what we have here is very simple. It's a Gaussian blur. It's a single line of code in OpenCV. So this is just basically blurring it using a kernel size of 11 by 11. So at every pixel, it's checking its 5 neighbors to the left and the right, and it's blurring or left to the or right or up and down and blurring appropriately. Here, what we have is thresholding. So as it's set up currently, anything below the threshold is being clipped out and replaced with straight black. So as I modify the threshold value, you see we get more or less of just a grayscale image of myself. We have different thresholding modes. So this is the opposite. So everything that is above the threshold value gets cut out and replaced with black. We have this where the threshold becomes the maximum value in the picture. So anything above the threshold gets brought down to the threshold's level. So as you can see, I slowly get consumed by a gray void until there is nothing left. We have this threshold takes everything above the value and turns it black, and anything below the value it turns it white. And this is the opposite, where anything below the value is black, anything above is white. Fairly simple. So using our thresholded value, we're going to do some dilation and erosion. So the way that this is currently set up, we are taking our thresholded image, which I can still modify. We are applying a dilation, which will increase the size of the sort of the white areas, or like the major kind of lighter areas, and erosion will erode at those whiter areas by increasing the darker areas. So if I increase the kernel size here, you'll see that the darkened areas of the image slowly are eroded as the lighter areas dilate. You'll see that it is a bit of a blocky effect, and this can be changed by the shape of our erosion or dilation. So we have squares, we have sort of cross shapes, and finally we have circles. Circles tend to not work so well on the higher kernel sizes. So we can see that we can do this, basically the opposite process with our erosion, right? So The reason that we have it set up with the dilation and the erosion is that we can use the dilation to, in a sense, remove some of the noise. So you can see that there's kind of a bit of noise sort of around my neck and on my hand and around like my shirt and stuff like that. So we can minimize or reduce that noise a little bit by applying a dilation, and then get back some of our shape by applying the erosion. And so we have the result is we get like a bit of like a cleaner shape in our final field. So next we'll look at feature detection. So the way the feature detection works is that it will look for high points of contrast. Specifically, what it's looking for is corners. The reason that corners are so important is that they're easier to track, right? Like so if we look at this grid, which I'll use again as a calibration target in a little bit, you can see that the algorithm, for the most part, it's only really capturing the corners of the grid. And the reason for this is as the grid moves around, right, the corners provide excellent anchors for tracking that motion. Because when a corner moves, it's just simply easier to identify. Whereas if you were to pick a point on the line and the grid moves, you may be detecting that original point that you picked, or you might be detecting a completely different part of the line. And there's really no way to tell because the feature detection algorithm is only really looking at like a small kernel at any given time. It doesn't really have the context of the entire image. It can't really say, it can't really know I am picking this point on the line that's 5 millimeters away from the corner. So it's easier for the algorithm to to take notice and keep track of corners. This will be very useful when we do our calibration. But before we get to the calibration, this is some background subtraction. So what this does is it keeps track of the past like dozen or so frames or something like that, and it looks for change, right? So as you can see in the left side, my background is all black, but sort of my outlines and my hands are very bright white and gray, and the more that I move, you kind of get kind of this lasting image in white. You may see the background sort of bloom white or gray a bit, and that's because my camera's adjusting the light settings as I move forward and backwards, and it's getting more light from this light behind me. So don't worry about that. If I were to stay as perfectly still as possible, eventually frames would stack up more and more. You kind of see that result is this very subtle black figure. And then as I move again, we have the white once more. Next, we're going to look at face tracking. Now I'm running this in a debug build, so the face tracking is a little slow. And this uses a pre-trained neural network with some standard face tracking patterns, and what it does is that it matches those patterns all over the place on the picture, and basically probabilistically determines is this a face based off of the results of matching the patterns against the picture. And as I said, the neural network is already pre-trained, and it returns the location of the face in the picture and about like how big the face is. So now that we've gone through all the basic tools and utilities of OpenCV, what we're now going to attempt is our camera calibration. So in theory, what this should do is that every camera, by nature, should have some level of distortion, because we can't really have orthographic cameras in real life. Our cameras are designed with the sort of pinhole model in mind, which is very useful, when we want to take a picture, but less useful when we want to scan objects. So we want to remove that distortion as much as possible, and to do so, we will use the checkerboard from earlier as sort of a model of what to look for. The program has in its insides an internal model of where the different points on the checkerboard should be, and so when I bring up the checkerboard, it's going to detect those corners from before from the feature tracking and sort of match those points that it detects versus the model that it has internally, and based off of the differences, it will be able to calculate the distortions of the camera and create a new sort of camera matrix, which we can use to undistort our camera feed. So the reason that I'm taking so long to bring up the checkerboard is because the way that this is set up, the process is divided into 3 sections. So a detection section, right? It's just looking to see if it can find the checkerboard pattern. If it doesn't, it just kind of moves on. A capture mode, where it will capture roughly 10 pictures, which it will then use for the calibration, and once it has those 10 pictures, it will calibrate the camera, and then after the calibrations, we'll get another window on the left showing the undistorted view. So, as you can see, when it detects the grid, it highlight all of the sort of corners, and it went through the calibration. And here is the main issue that I've come across with this challenge. This is where the challenge has defeated me. When I first started calibrating, like 4 or 5 hours ago now, my calibration error was somewhere in the 40s. So a very huge error, right? The calibration error should be as close to 0 as possible. I've managed to figure out some of the bugs that I was having, and managed to reduce my amount of error to about 1.5, as you can see here. The results of my undistortion are questionable, as you can see in the left-hand side. And I've kind of reached my wit's end with trying to figure out why this isn't working. Some theories are that simply my calibration target is a little bit unreliable. It's just standard grid printed on some paper that I'm holding up with my monkey hands. And so the paper itself probably has some distortions that aren't part of the camera. Alternatively, there could be something going on in my code that I'm unsure what it would be at this point. It's the night before submission, and I'm running out of time. And that's why I've also been unable to do the stereo calibration. I'm not even sure where I'd begin with that. If that would require maybe like image sets, like paired image sets, or I've currently been doing all of this with the live feed, so I don't know necessarily how I'd go about that, as I only have the one camera. As it is, this is where I have reached in this challenge. So, thank you for your time. I hope you have a good night.